Hi, today we're going to talk about the real number system. It's pretty fun to see how all these numbers fit together. So I have up on the screen to start with this worksheet that you should have already printed off. And as I go through the lesson today, I'm going to talk about all of the things that are on this worksheet. And if you just want to jot down a note or two as I go, that would be great. And sometimes I go kind of quickly, and you can come back to some of these questions after I'm done teaching or go back and rewatch the presentation. So some of the things that you'll hear right as I'm talking are things like, what is another name for counting numbers, and what are some examples of counting numbers. Something you might want to do after you've had some time to think about it is, when do we use counting numbers, and what is the difference between whole. Okay, so let's talk about the real number system. Let's start off by talking about the counting numbers. So the counting numbers are the numbers that we started with. 1, 2, 3, 4. They go on and on and on. They keep going clear to infinity. So, the number 1,000,000, 1,000,001. All of those numbers are included in the counting numbers. They're easy to identify. They're whole numbers that we started learning, and we learned all the basic operations in math with these numbers to begin with. So addition, subtraction, multiplication, and division, those were all pretty simple as we began to learn with those numbers. Okay, so then we build on that set of numbers and we introduce the whole numbers. And the reason why we kind of expanded numbers from when numbers began to be important was we needed something to represent nothing. And you probably haven't spent a whole lot of time thinking about it, but the number 0, which really represents nothing. So the number 0 is the one number that distinguishes the whole numbers from the counting numbers. And so that brings me to my second point. The counting numbers are also often called the natural numbers because it's very natural to have something that we can identify with a value, 1, 2, 3, and so the natural and counting numbers are all of these numbers from 1 going to as high as you could possibly count, and then some. And then we add the whole numbers, and so that's when we add the number 0. So the whole number system still doesn't quite cover everything that we need. So we've moved on, and now we have integers. So integers have all of the whole numbers because it includes the number 0, and then it also has all of the counting numbers or natural numbers. So you can see that the whole numbers included the counting and natural numbers, and now the integers include the whole numbers and the counting numbers. So the integers also include all of the opposites of these numbers. And it's really fun to be able to start learning to add and subtract and multiply and divide with negative numbers. You're going to love that as we get into learning some of that stuff. But the importance of having a way to represent negative or less than 0 was for things like distance between an airplane flying high above the sea and maybe a fish swimming down deep in the sea. So what we could do is we could say sea level starts right here at 0, and our little fishy is swimming way down deep in the water below sea level, and our airplane's flying way up high in the sky above sea level. So then we can start to identify this distance. And you might be able to see negative numbers in other ways. You can see them on temperatures. You can see them in sports games. Maybe the Super Bowl you just watched and they had some negative yardage. That meant they went backwards from where they had started at this starting point. And after the integers, we add, so now we have the integers, the whole numbers, the counting numbers. Now we're going to add fractions. And this is awesome because this shows a portion of something. So a rational number is a ratio or a fraction of two integers. So remember, those integers are our whole numbers and their opposites, all our counting numbers. And you can see right here, our whole number is 0 and our integer 0, and that can't go in the denominator. If that goes in the denominator, we have something undefined, and we don't want that. So we make one little exception right here, and we've introduced our rational numbers. Now, rational numbers include any number that can be written as a fraction. So the number 5 can be written as a fraction, even though we can see right here this is a counting number. It's also a rational number, because if we write a 1 under the 5, we've made it a ratio, and so on. And you can see we have repeating decimals, we have terminating decimals, we have positive fractions, and we have negative fractions. And all of these fall into the rational number system. And then we kind of expand out. So all of the numbers we've talked about so far are rational numbers. Your counting numbers, your whole numbers, your integers, and now all the fractions or ratios of those numbers. Those are all rational numbers. And then we kind of, within our real number system, so these are still real numbers, but they're not rational numbers. So they're separate from these numbers. They're called irrational numbers. And let's take a look at what makes an irrational number irrational. This is a number, it's pi, and it represents the circumference of this circle, the ratio of the circumference of this circle to its diameter. And if we were to divide this out and do this long division, we would get a number that begins like this, 3.1415, and this number would go on and on and on forever. I remember a math teacher once telling me that people had gone insane feeling like they could get to a point where this number would have to repeat itself, and it simply doesn't. And because of the nature of this number never repeating, it is called an irrational number. And we have other irrational numbers as well, like the square root of 2 that repeats itself indefinitely, and the square root of 3, and the square root of 5. So you can see these numbers created a little bit of havoc when they were first introduced. So here's a cute little comic. So they have this ancient Egyptian, and here they've tied a weight around his ankle and they've sunk him because he suggested this idea that the square root of 2, representing this little fishy's fin, is an irrational number. And they were kind of worried about the idea of a number not repeating itself. And so it was frightening. Today we know it's exciting. It opens up all sorts of possibilities for math that we can do. Amazing math. So there's a quick introduction to our real number system. And now I'm going to walk you really quickly through the assignment that I would like you to do. Okay, so let me quickly walk you through an example of the assignment that you're asked to do. So the assignment that you're asked to do is to create a picture that shows me that you understand the relationship between the numbers in the real number system. And so this example right here shows a rainbow. And the rainbow begins right here with this red, and these are the counting numbers, 1, 2, 3, and so on. And then within this real number system, I then add the whole numbers. So I have all these counting numbers, but I've grown a little bit bigger, and now I also have the number 0, so my whole numbers. And then my integers, so these include all of my whole numbers, and then all of the opposites of my counting numbers. And then I have my rational numbers. So these are all of my negative numbers that can be made into a fraction of two integers. So right here I have a terminating decimal, I have a negative fraction, I have 0, I then have 3, which is a counting number, but I've made it into a fraction, and then the number 5. And then I have the top that kind of titles my picture and says this is the real number system. And now, within the real number system, I can also have these irrational numbers. These don't include any of my whole numbers or my integers or my counting numbers. They are numbers that are separate. So they're non-terminating decimals, and they are things represented by this little symbol right here that represents pi, that number that I showed you earlier, and then the square root of 2 and the square root of 17. Another really quick example is this one right here, kind of an underwater scene. So we start with our counting numbers right here, 1, 2, 3, and then this little fishy is eating these. So this little fishy includes all the counting numbers and then also the number 0. So this is the whole numbers. It has all the counting numbers and then the number 0. And then this fish was hungry, so it ate this fish. So the integers, they have all the whole numbers, all the counting numbers, and now they have all the opposites as well. And then this great big fish, so this great big fish is our rational number. So all of our fractions and their negatives, we have terminating decimals and repeating decimals. So if you wanted to write any of those as examples in your rational numbers, that works as well. And then within my real number system, I have irrational numbers as well. And so I represented those as kind of a boat. So they're out here on the ocean with our real numbers, but they're not rational numbers. They are separate. They are their own thing. So that's just one idea. Another idea might be something like create a city, and you can have a person be a counting number. And then that person lives in a house, and the house is the whole numbers. So the house also has a window maybe that's a 0. And then the house lives in a neighborhood, so you would have all of your houses maybe with addresses that were positive and negative integers. And then those houses were all within a city on a map, and the city was your rational numbers, maybe with some streams and some maybe hills, a park, something like that. And those would have all of your fractions, your terminating decimals, and your repeating decimals, also all of the negatives. Those are all rational numbers. So then maybe to represent your irrational numbers, you could do something like maybe an airplane flying above. So it's not really down there in the city where your rational numbers are, but it is still part of the real number system. And so on your airplane you could have the symbol pi or the square root of 17. That would be a perfect example. Have fun with this. Think about it. Have fun with these numbers. And if you have any questions, let me know. Thanks.